What's up guys, it's your boy XX back with another FRQ video. Now, last video, you fans hit 2 likes on that last video. So, as a gift, I'll be uploading 5 straight videos today for your enjoyment. Now, if we hit 3 likes this video, I'll have something special as a surprise for you fans. Now, back to the video. This is FRQ set 5, number 1. A block of mass 2 kilograms is attached to a light spring that is wrapped around a cylinder. The mass has a mass, blah blah blah, and the radius, blah blah blah, and it can rotate around this rod through its central axis, and is initially at rest. Part A, using integral calculus, show that the rotational inertia of the cylinder about its central axis is 1/2 mr squared. Ooh, shadow. Anyway, you know, or at least you should know, that I, moment of inertia, equals the integral of r squared dm. Now, we can substitute dm by using the density formula, P equals mass times velocity, P being the density. And the density also equals the change in mass over the change in velocity. And we can, to isolate for dm, we can multiply dv over. So we get dm equals density times dv. You'll add that here. R squared, m equals density times dv. Okay. And we can move the density over because it's a constant. Okay, now we want to replace dv with dr. So what equation has both v, volume, and r, radius? Volume of a cylinder. Volume of a cylinder, if you don't know, is pi r squared, the area of a circle, times its height. And if we take the derivative of both sides, we get dv, the change in volume, equals two pi r times h times dr. And we can just plop that right in too. I equals density integral r squared 2 pi r times h dr. Now, since 2 pi h is a constant, we can also move it to the other side, outside the integral. P 2 pi h. And r squared times r is r cubed dr. So we can set our bounds of the integral to r and 0. And when we take the integral of that, we get, this stays constant. The integral of r squared, r cubed, with respect to r, is r to the 4th over 4. And once we plug these in, we'll get I equals density 2 pi h times r4 over 4. Okay, we'll simplify that. This crosses out and this becomes 2. So we get 1/2 density pi h r to the 4th. Now, we need to end up with the answer 1/2 mr squared. And we have all this mumbo jumbo. But what we can do is go back to this density formula, right back here, dm over dv. And we have dv right here. Wow! So our new p equals dm, plug dv in, 2 pi rh. Now we can plug this density back into here. I equals 1/2. This is dm Did I mess up? Yep. Okay. My bad. Okay. P equals mv. And v is pi r squared times h. Used the wrong one. So m over pi r squared times h. And we can plug that in. So we end up getting I equals 1/2 m over pi r squared h times pi h r4. We can cross out pi, we can cross out h, we can cross out r squared and reduce r to the 4th into 2. And in the end, we get 1/2 times m, and this is 1/2 times r squared. Ta-da! Part A. This one's part A. Okay. That was a tough one. Alright, next. Turn this over. Part B. Part B says, calculate when the block is released from rest and the string unwinds, causing the cylinder to rotate on the rod. So what's happening is, we let go of the block, the cylinder rotates, and the block slowly goes down. So we're supposed to calculate the linear acceleration, the net torque, and the tension. So the first one, calculate linear acceleration. When the cylinder is spinning, there is a torque. So we'll use a torque formula. Net torque equals moment of inertia times alpha, or angular acceleration. Now, there is one force touching the cylinder that's providing the torque, which is tension. So we'll use that, tension times r, the radius, equals, I equals, as we did earlier, 1/2 m r squared. We'll actually use the big M because there are two different M's. Big M is the cylinder, small m will be the block. And alpha is equal to A over R, because A acceleration, linear acceleration equals R times angular acceleration, so I just divided R over to get that. Ta-da! And I moved it here. Woo! Okay, we can cross out this R and that R, and we can cross out that and that. And we are getting tension equals 1/2 MA. Now, what is tension? We'll move on to the Newton side of the system. So, when we look at the block, there is two forces touching it, tension pulling it up, and force of gravity, Fg, pushing it down. And since the block is moving downwards, Fg is larger than the tension. So we have net force equals Ma. Two forces are Fg, the bigger, minus T, the smaller, equals Ma. I say for T, we get T equals Fg minus Ma, and T equals Mg minus Ma. So we can plug this up to here. Mg minus Ma equals 1/2 Ma. Okay, so the mass is 2. G is 9.8. This mass is also 2. A equals 1/2. Mass of the cylinder is 2.5 A. So you get 19.6 minus 2A equals 1.25 A. Move 2A to the other side by adding it to both sides. 19.6 equals 3.25 A. Divide 3.25 and we get A equals 6.03 meters per second squared. That is our linear acceleration, part 1 of part B. Now part 2, if you remember, asks find the net torque. So once again we have net torque equals I alpha, and we're not going to break down net torque this time because we need that for our answer. This will equal 1/2 mr squared, that's AR. Cross out this, cross out that, we get that. Okay, net torque equals 1/2 MRA. Okay, 1/2, M is 2.5, this is half, R is 0.4, and A, as we found out in the last problem, 6.03. Multiply all that together, and we get net torque equals 3.02 newtons times meters. Part 3 asks to calculate the tension of the string. So we can just use this equation since we have all we have mass, gravity, and acceleration. T equals mg minus ma. Tension equals 2, 9.8 minus 2, 6.03. So tension becomes 19.6 minus 12.06, and we get tension equals 7.54 newtons. Okay. Part C. Part C asks, sketch the linear momentum of the cylinder as a function of time from the moment the mass is released shortly to after Ts. So we're going to graph the time from here to here. Ts is when the block has stopped unwinding, basically when it's reached the bottom. So linear momentum equals I times omega. Now, I is always a constant, so we can cross that out. And we're left with linear momentum is directly proportional to omega. Now, omega is increasing at a constant rate because its angular acceleration is increasing at a constant rate. And therefore, as time goes by, linear momentum is constantly increasing because the angular momentum, the angular velocity is constantly increasing. So, here's the graph. Whoa. I want to copy the graph because I have it right here. Anyway, part D. Bunch of words. Solid cylinder is replaced with a hollow cylinder. A hollow cylinder has an moment of inertia of mr squared. So basically everything is the same except the solid cylinder is now hollow. So same mass, same radius, same position of everything. Now, there's a new time when it reaches the bottom, when it completely unwinds. And is it greater than the time it takes for a block to go all the way down in a solid cylinder? Now, this is the moment of inertia of a hollow, and this is the moment of inertia of a solid. So as you see here, the moment of inertia of the hollow is twice as much as the moment of inertia of the solid cylinder. And the more inertia you have, the more resistant the object is to change, which means it takes more force to get it moving, which means it takes more time for the block to go down because it's harder to move the hollow cylinder. So basically, yes. Anyway, that's it. See you in the next video, FRQ set 5, number 2. This is your boy XX Killer, XX Silent Killer, XX, and I'll see you next time.